This slide introduces the Leetcode problem, number of ways to arrive at destination. The image visually represents the problem statement, showing the city map with intersections and roads. We'll break down this problem step by step. Here's the complete Python solution using Dijkstra's algorithm. We initialize a graph represented as an adjacency list, and two arrays, dist to store the shortest time to reach each node, and ways to store the number of ways to reach each node in the shortest time. We start with a priority queue, PQ, containing the starting node 0, with time 0. The main loop processes nodes from the priority queue. For each neighbor of the current node, it checks if a shorter path is found. If a shorter path exists, we update the dist and ways and put the neighbor in the priority queue. If the new time equals the current shortest time to the neighbor, it means there's another way to reach the neighbor with the same shortest time, so we add the number of ways. Finally, we return the number of ways to reach the destination, node n1. The modulo operation is used to handle potential integer overflow. Here, we're focusing on the initialization part of the solution. Graph is an adjacency list, representing the city's road network. Each key is a node, intersection, and the value is a list of tuples, where each tuple contains a neighboring node, and the travel time to that neighbor. Dist is initialized with infinity for all nodes, representing that initially we don't know the shortest time to any node, except the starting node, node 0, which is set to 0. Ways is initialized with 0 for all nodes, except the starting node, which is set to 1 because there's one way to reach the starting node from itself by taking no action. PQ is a priority queue that stores tuples of time, node. It helps us efficiently pick the node with the currently shortest known travel time. We initialize it with 0, 0, representing the starting node with a travel time of 0. This is the core of Dijkstra's algorithm. The while loop continues as long as the priority queue PQ is not empty. Inside the loop, we first get the node U with the smallest time from the priority queue using heapq.heapop. If the extracted time is greater than the currently known shortest time to reach U dist, it means we've already found a better path to U, so we skip this iteration. Then, we iterate through the neighbors V of node U. For each neighbor we check two conditions. First, if the time to reach U, plus the time to travel from U to V, is less than the current shortest time to reach V, we've found a shorter path. We update dist and ways, and we push V onto the priority queue. Second, if the new time is equal to the current shortest time to reach V, it means there's another way to reach V in the same shortest time. So we update the number of ways to reach V by adding the number of ways to reach U. We use the modulo operator, 10 to the power of 9 plus 7, to avoid integer overflow. Finally, after the loop finishes, ways 1 contains the number of ways to reach the destination node, n1, in the shortest amount of time. Let's talk about the time and space complexity of this solution. The time complexity is big O of E plus n multiplied by log n, where n is the number of nodes, intersections, and E is the number of edges, roads. The log n factor comes from the operations on the priority queue, heap. Building the graph takes OE time. Dijkstra's algorithm itself visits each node and edge at most once. The space complexity is big O of n plus E, mainly due to the adjacency list used to represent the graph OE, and the dist and ways arrays, and the priority queue which can store all of the graph's vertices, oxygen mononitride. Thanks for watching. If you found this helpful, please like, subscribe, and comment below with any other Leetcode problems you'd like to see explained in this series. If you'd like to help me continue making these videos, you can donate at buymeaboba.com, link in the description.